All right, well, my friends, in this thermodynamics problem, we're going to use the expansion coefficient to determine how many more grams are in a liquid when we change the temperature. So we're going to use the expansion coefficient with a change in temperature to determine something. And in this case, it's how many more grams of gasoline. So this is the question. So we have gasoline has a density of 720.8 kilograms per meters cubed at 25 degrees Celsius. If you fill up your car in the winter, at negative 10 degrees Celsius. This is in Canada. I'm from Canada, so it gets cold in the winter. How many more grams of gasoline are in every liter of gas than the summer? So we'll say that's 25 degrees Celsius. That's all we have to go on. In our summers, it's a lot hotter, but anyways, here we go. The expansion coefficient of gasoline we're given here is 9.50 times 10 to the negative 4 per Kelvin. So we're going to start off, and often with expansion coefficients and isothermal compressibility coefficients, if you're given those in questions, it's often good to start off with the definition. So the expansion coefficient is defined as 1 over the volume times the partial derivative of volume with respect to temperature, holding pressure constant. Now we're going to multiply both sides by dt to get alpha dt equals dv over v, and we're under constant pressure conditions. Now we can integrate, so we're going to do a couple things here. We're going to integrate both sides, okay, so we're integrating both sides. So this side, now there's no integration symbol here because we're assuming that delta V is approximately equal to dV, and we're doing this because this is a liquid. It's not a gas, it's a liquid. So we're assuming that the volume doesn't change much. And for liquids and solids, that's a pretty good approximation. So the integral of this, dV over V, is the delta V over V. And we're also assuming that the expansion coefficient is constant. It does change, but over this small temperature range, we're going to assume it doesn't change, so it comes out of the integral. Okay, so if we rearrange this and integrate, so the integral of this is delta V. So delta V over V equals the expansion coefficient times delta T. Now at this point, we can plug some things in. We know what the value of the expansion coefficient is. That's given here. We know what the change in temperature is, final minus initial. We're in Kelvin here. I don't have to convert to Kelvin, but because it's a change, but it's always good practice just to convert to Kelvin anyways. If you're in Kelvin, you'll usually never go wrong. So this gives us a delta V over V equals negative 0.03325. So the change in the volume is about a little over 3% smaller. So about 3.32% lower volume. Multiply this by 100. So the volume at negative 10, it's going to be 0.9668 times the volume of 25 degrees Celsius. So what this means is that, like, if this was a 1, this volume would be the same as this volume. If this was 90, 0.9, if this was 90%, 10% lower, you would have 0.9 if it was 10% lower. But because this is 3.32% lower, we got to take 1 minus the 3.32%. So the volume at negative 10 degrees Celsius is 96.68% as much as the volume at 25 degrees Celsius. I hope that makes sense. I hope that's not like, let me know if that's confusing or not. Okay, so at this point, we're going to look at the densities because we want to know how many more grams there are for every liter. So the density at 25 degrees Celsius is 720.8 kilograms per meters cubed. That's what's given here. We want to know how many grams there are per liter. So we'll multiply by some conversion factors to give us 720.8 grams per liter. It's the same, but it's important to do these conversions. So to get the density at negative 10 degrees Celsius, we take the density at 25 degrees Celsius and make sure it's 3.32% larger. Since the volume is smaller, this percent smaller, the density has to be 3.32% greater. So we take this number divided by the 0.9668 to make our density 3.32% larger. So that would be 745.6 grams per liter. Okay, so now we know how many grams there are in every liter. To find out how many more grams of gasoline are in every liter of gas, we take the difference. So the extra grams at negative 10 degrees Celsius is the difference. So we'll take final minus initial, 745.6 minus 720.8 grams. So gasoline at negative 10 degrees Celsius contains an extra 24.8 grams compared to gasoline at 25 degrees Celsius. So we get kind of more bang for our buck if they cost the same amount per liter. All right, so thanks for working through this problem with me. I hope it's given you some value. I hope it'll help you on your other problems and exams and quizzes and assignments and things like that to give you further insight into thermodynamics. Just note I've got tons and tons and tons of other videos on thermodynamics and other aspects of chemistry and physics. Hang in there. This might sound corny, but chem is try. So the more problems you try, the better you'll get at chemistry and physics if you're taking this thermodynamics in a physics course. The more problems, the better. Thanks again for watching this video, and I'll see you in the next one. Cheers.